Hopefully everyone is good this morning. So we are going to start on the first section, which is the general power formula. So first, I think we'll do a bit more of a review of derivatives, and then we'll go to the general power formula. And is there anything else I'm forgetting? And let me know if anyone has any questions. Okay, so let's share screen. So this will be our first integration formula. But again, first we'll look at its corresponding derivative formula. Can I write with this thing or can I not write with this thing? Hold on, give me a second. Annotate. Oh, good, I can draw on a picture too, that's good, okay. Okay, so here's the formula right here. So this is the derivative formula. So it basically says that if you have x raised to an exponent and you want to take the derivative of this, basically you take the exponent and you drop it down in front of the number, and then you subtract 1 from the exponent. So that's the rule for exponential functions. So it's a pretty simple rule. Drop your number down, and then the exponent, subtract that by 1. So now we're going to look at the general power formula, which is basically you could view it as being the reverse of this formula. Because remember, that's one lens that you could view these things, is that a derivative kind of takes you in one direction, and an integral is like an antiderivative that returns you to where you originally were. So I just want to put that context in there, that the formula I'm about to present is basically just the logic it's using is that it's the reverse of this formula. So let's just go to the lesson, new share, general power formula. So this is chapter 28, 28.1. Hold on, darn it, now it's annotating everything. Hold on, I have to turn this mouse, and I'll just use the actual PDF. Move out of the way. Oh, good. Let's see. Oh, here, yeah, it's in red. It's easy to see. Let's see, black. Okay. Okay, so this just mentions that integration and differentiation are inverse processes, although ironically, or does it count as irony? In reality, integration was actually invented first, or I should say discovered first. And then derivatives actually came a lot later. And then Isaac Newton, a physicist and mathematician, discovered the fundamental theorem of calculus, which basically says that derivatives and integrals are reverse processes. So this mentions that now we're going to look at some particular formulas for figuring out integrals. And it mentions what I mentioned previously, that if you're not super caught up on, what you guys did before, check out chapters 23, 25, and 27. So that's some basic review on derivatives and stuff like that. So here is our formula right here. Maybe I should do this in a whiteboard. This is fine for now. So here's the formula. The integral of, hold on, let me fix this. Nope. Nope. I guess that's okay. Okay. So the integral of u raised to the n. Darn it, I hate this writing thing. Sorry, I'm trying to find the best. Okay. It's too thick. Okay, that's fine. Yeah, sorry, this writing thing is hard, so a lot of the times my writing is pretty indecipherable. So you have an integral of u to the n du, where u is some function, n is some number. And in this case, the formula is that you take u and you add 1 to its exponent, and then you divide by that number. So you just, for the exponent, n plus 1, and then you divide by n plus 1. And again, the logic is that it's reversing the previous formula that we looked at. It doesn't quite look like it's the reverse of the previous formula, but we'll check that and we'll confirm that it is the reverse of that previous derivative formula that we saw. And then you always have to remember the one thing that I always forget, which is the constant at the end of your integral. Whenever you integrate something, you have to add plus c at the end of it, because when you take the derivative of a constant, it diminishes to 0. So when you take the integral of something, you have to add in that constant because you could have hypothetically had a constant there. And I always forget, but you got to just remember. My advice would be like at the end of every assignment and test, just formally go through your questions and just add your constants and make sure that you have them. But it's just a little extra thing to remember. You just write plus C, and that's yeah. And this just notes that in this case, n cannot equal -1, because then if you look at the formula, you'd get division by 0, which, as everyone told you in high school, will destroy the world if you divide by 0. So yeah, the n equals -1 case, that's like another formula. So we'll look at that later. So before we keep going, let's confirm that this formula actually is the reverse of that previous formula. So how do we confirm that? Well, what you could do is you could take the derivative of your answer, this right here, and if everything is correct, you should end up with what is inside the integral. That's a standard way of checking your answer. Once you integrate something, you can take the derivative and just see, does it return you back to what you had inside the original integral? And if it does, then you're all good to go. So in this case, what we're going to do is let's take this right here. Let's take the derivative of that and see if we end up with un du. And if we do, then it's a valid formula and we're good to go. But let's do this on a whiteboard. And this part right here is just a bit of an extra thing. It's just checking to make sure that everything's working. And then we'll look at some actual examples. New share. Oh, hold on. If I'm going to do this, I need my laptop in front of me. Sorry, just give me 2 seconds. I have limited room over here. Okie doke. So let's go to whiteboard. Okay, so let's take, what was the answer? It was u to the, why is it always changing? Okay, it was u to the n plus 1. That was our little final result. And then we had n plus 1 on the bottom. We had our constant. And what I want to do is just take the derivative of this. And again, we should end up with what was originally inside the integral. And that will confirm that everything's good to go. So let's take the derivative of this. I'm just going to put brackets around it. And for the format, let's just use d over du. So that just denotes that we're taking the derivative. So in this case, we used that previous derivative formula where the exponent drops down and then you subtract 1 from the exponent. So things will get a bit messy in here, but it'll all resolve itself. So, okay, take the exponent, which in this case is n plus 1, and drop it down. So you got an n plus 1 on top now. You still have that n plus 1 on the bottom. And then the next step was subtract 1 from the exponent. So in this case, and again, it's going to get messy, but it'll resolve itself. You'll get n plus 1, and then you subtract 1 from that. So we're just kind of using that previous derivative formula on this. And for now, it looks kind of ugly, but yeah. So in this case, some stuff cancels out. The n plus 1 cancels out on the top and the bottom. That's good. For the exponent, you have n plus 1 minus 1. So the plus 1 and the minus 1 cancel out. So that's good. Oh, I should put du right here. You got to have your little dx's and your du's. Yeah, basically for formatting, but also for practical purposes. And surprise, surprise, you end up with u to the n du. Ta-da! So we've just proven that, yes, indeed, that original derivative formula we looked at is the opposite of this integral formula. So I always like to establish the internal logic of what we're doing rather than taking it for granted. And there is another thing I do have to note that is extremely important. Let me just clear this part. Let's see. What was I going to note? Let me write down the formula just so we have it. So integral of u to the n du equals u to the n plus 1 divided by n plus 1 plus your fancy constant. So there is one thing that's really important to note is that the integral right here is set up in a very, very, very specific way. You can only use this formula if it's set up in this specific way. So let me elaborate. The format we always have is that you have this function u raised to an exponent n, and then we specifically have du sitting right next to it. So you have to actually have, if you have this function raised to n and you want to use this formula, you actually need this part right here. It's absolutely essential. You need whatever the derivative of u is, you need that sitting next to u. Otherwise, the formula just doesn't work. So a lot of the times you have to check, even before you use the formula, is it actually in the right format? Because sometimes you might have something like, you might have the integral of u to the n, but you don't have any du sitting next to it, and there's just nothing you can do. You need that du, which stands for the derivative of u. So you need that. So that's important to note. And for each example, we're always going to check that it's actually in the correct format, that it's a function raised to a number, and then the derivative of that function sitting right next to it. Yeah. Mm-hmm. Absolutely, yes. Yeah, someone just asked if n is like, for example, 2, would what I'm saying still apply? Yeah, because n in this case just represents whatever exponent your function happens to have. So you always need that du right there. So let's see. So the rest of this is doing examples. I want to start off with an easier one though. Let's start off with a really easy one. Let's just do one that is, let's do the integral of x to the 6 dx. This one, you don't have to worry too much about that because the function is just x. Like it's an exponential function, but within that, it's just x. So yeah, in this case, you have dx, and it's kind of what I previously said is kind of trivial, and you don't really have to worry about it in this case because it's such a simple function. So in this case, everything's already set up. You got x, you got it raised to the 6. You got a dx, which is, it technically means derivative of x. But in this case, everything's in regard to x, so they literally just write dx. So again, the dx part is like, it's like formatting. It's also for practical purposes. So in this case, the answer, or applying the formula, is pretty easy. Add 1 to the exponent and divide by that number. So x to the 7 divided by 7, plus your constant. And that's all you have to do for that one. So the actual formula is not too bad. Yeah, this is the simplest example I could think of. And then of course you could always check your answer. In this case, checking the answer is pretty easy. You just take your answer, again, take the derivative and see if it returns you back to what you previously had. Since this is the first example, let's check it and let's see if it works. Let's see. Okay, so our answer is x. And you don't have to do this checking step. It's just for illustration. Because a lot of the times checking your answer can be just as laborious as getting the answer. And a lot of the times it's not even practical to check the answer in this regard. But sometimes it's very easy. Okay, so x to the 7 over 7 plus our constant. So let's take the derivative of this and let's see what we get. We should end up with x to the 6 dx, and that's just confirming that our answer is good. So take the derivative of this. So the 7 will drop down. So 7 will drop down, and then subtract 1 from the exponent, so that'll be 6, and then there's a 7 on the bottom already. And then the constant, the derivative of a constant is just 0, so don't have to worry about that. And then voila, this cancels, you get a car, and then yeah, wow, that's a dated reference. And then you get x to the 6 dx. So indeed, the formula does work, but again, you don't always have to take the time to check it like that. It's up to you. So that's one good example, and now let's move into a couple that the textbook has. Let's get rid of this. Okay, so this one is, and I guess I should refer everyone to the, so yeah, 28.1, page 850. But I'll write down the question regardless. I'm not sure if everyone has the textbook. So the integral is integral of sine raised to the 3, and then cos x dx sitting next to it. So when you initially look at this one, a lot of people are probably thinking like, this one looks like a nasty one. It doesn't look like it's going to be an easy one. You got like a sine, you got a cos. Everyone hates trig. What the heck is going on? But this one's actually really convenient because it is in the correct format. Let's illustrate that. In this case, u is sine x. So why don't we just, off to the side, let's just label everything. So u is sine x. That is our u function. N is 3. That's our exponent in this case. And in this case, du is actually this part right here, because if you'll recall from last lesson, the derivative of sine is cos. So we actually do have it in the exact perfect format. It actually is in the form u to the n du, because in this case, cos dx is your du part. So du equals cos x dx. And again, that in this case, you kind of just have to have it memorized that the derivative of sine is cos. You just have to kind of know that, or have a reference somewhere. So it is set up properly. Sometimes that's the main thing that you have to check, and then doing the actual formula is pretty easy. So in this case, let's see. Maybe for further illustration, let's just write everything in terms of u. So this is in the form integral of u to the 3 du. So that's the form that it's in. So far, so good. And now let's just apply the formula. So let's add 1 to the exponent and divide by that number. And then at the end, I'll put like the sign back in, because sine was the original function. I'm just using u, so it looks a bit simpler. So let's do u to the 4 over 4 plus your constant. Very good. And then again, at the end, put sine back in. So this is going to be sine to the 4 over 4 plus c. And that is your answer. So in the process of integrating, the cos x dx part kind of just like folds in on itself and disappears and doesn't appear in your answer. So that's okay. It's a correct answer. So sine to the 4x over 4 plus c is perfect. You could write this a little bit differently. You could just write it as, you could put the 1 over 4 out in front. That's just, I mean, it makes absolutely no difference. It's just formatting. I like this one better. I like having the number out in front rather than just straight up having it on the bottom, but it's like tomato. It's totally up to you. So that's what we do for that one. Does anyone have any questions so far? So what do we think of this? Not too bad. Okay. Let's see some other examples. So I want to do a couple more simpler ones before we go to the ones they have in the textbook. We'll have to do some additional derivative formulas. But let's do a similar one to this one. This is number 4 in the exercises on 851. So get rid of this. Yeah, it's almost the same question, but it's a little bit different. So it is cos to the 5, is it a 5? Cos to the 5x. Cos to the 5x, and then sitting next to it is minus sine x dx. So let's check to see if this is in the right format. It's always good just to get your bearings, establish u, establish n, take u and take the derivative and see if that's what's sitting next to u to the n in your integral, because you need it in that particular format. So u is going to be whatever function is raised to the exponent. So I know that u is cos in this case because that's the one the exponent is applied to. So u equals cos. Good. N in this case is 5. And now let's check du. So if u is cos, then du So the derivative of cos is minus sine. I remember that from Tuesday and from university. Minus sine x dx. So if you compare this to your integral, everything is actually in the correct format. It's technically in the format integral of u to the, in this case, 5 du. So we're good to go. So add 1 to your exponent, divide by that number, and then kind of put your original variables back in there. So again, a lot of these can look really, really messy and ugly, especially since you have a minus sine x dx right here. But in this case, that entire thing is just du. So yeah, it's all good. So this will be u to the 6 divided by 6 plus your constant. So that should be, what's u? Cos. So that's cos to the 6 over 6 plus c. Very nice. So hopefully everyone's getting the hang of how to do these. Yeah, I always recommend establishing all the variables, especially as things get more complicated as the course progresses. I do that stuff. Even if I was doing a question by myself, I would probably do that establishing stuff, unless I was really confident in just directly getting the answer. So let's look at, are there any other ones that are interesting? Let's do, let's do number 8. This is another good reason as to why you should try to memorize some of the standard derivative formulas, because if you have them memorized, it's easier to see when this is in the correct format and when it's not. Because if you don't know any derivatives, it's going to be tough to evaluate these. Okay, so this is secant to the 3x, and then sitting next to it is secant x tan x dx. So this is another one that looks kind of ugly, and you could look at it and be like, how do I even use the general power formula on this? But don't worry, it'll all work out. So u should be secant, because again, that's what the exponent is applied to. So let's put that in. So u equals secant x. And in this case, it's just 3. I don't know if there's much point in writing that. It's just a number. The important thing is to figure out du, and hopefully it'll equal this whole thing right here. Otherwise, our formula is, or otherwise our integral isn't even in the correct format. So we know that u is secant. So what is the derivative of secant? Let's check I'm just going to double check. I mean, obviously it's going to be secant tan, but just to be fair, I'm going to check on our previous formula sheet. So what is the derivative of secant? It is, yes, it's secant x tan x. Perfect. Secant x tan x. Good. So it is in the correct format, not surprisingly. So this is in the form. So let's just write it in terms of u, because then at least it looks a lot simpler. Integral of u to the 3 du. Good. So that seems to work out. So that's the same as what it was. So that's good. And now you just apply the general power formula. So you'll get u to the 4 divided by 4 plus your constant. And now let's just write it in terms of the original functions. So this should be secant to the 4 over 4 plus c. So it's up to you if you want to switch it to u and then apply the formula and then switch it back. A lot of people can just directly apply the formula. So it's up to you. As long as you get this as your answer, you're good to go. But I just thought for illustration, it's just nice to see this in terms of this to just confirm that it's good to go. Okay, so let's go to some of the examples in the textbook. I wanted to do those last because, again, some of them refer to some derivative formulas that we'll have to establish. Oops. Oh well. Okay. Let's see. Which one do I feel like doing? Let's do. Ooh, this is an interesting one. Oh, that's a weird one. Let me read this for a second. So we got that, and then we got that, and then that's good to go. Okay, let's do this one. Clear. So this is another one involving trig, but this one definitely is a weird one. When you first see it, it doesn't even look like it applies to the general power formula, but it does. So this is 2 times the square root of 1 plus tan theta. Sometimes they use x and sometimes they use other variables. Even from example to example. If I was them, I would just stick with 1. Although theta makes sense because theta typically denotes an angle. So that makes sense in terms of trig. So this is a square root of 1 plus tan theta. And then next to that is secant squared theta. And then you got your d theta at the end. So in this case, it's like, what the heck is going on? You know, I see an exponent of 2, but it doesn't even look like. So this one is definitely a bit tricky. So you have to establish what is u and what is du before you can, of course, solve the question. In this case, I'm going to change the format of this a little bit. So you see that there's a square root around this part. A square root is technically just an exponent of 1 over 2. You could write any root in terms of exponents. So in this case, you could write it differently, and that will kind of illustrate why we can use the general power formula here. So for this, I'm going to replace the square root with an exponent of 1 over 2. So we got that. So to 1 to the exponent of 1 over 2. And then I'll keep everything the same for now. So in this case, we actually do have 1 plus tan theta raised to an exponent. It didn't originally look like it because they were using the square root format. But again, a root is just an exponent that happens to be a fraction. So in this case, you could always take a square root and just write it as 1 over 2 as an exponent. So in this case, it's a little easier to see that this part right here is going to be your u. And then this part right here will be your du. And n will just happen to be 1 over 2. So this one, when you look at it, you're like, what the heck's going on? But a little bit of format changing, and it becomes a little more clear that, yes, it will work. N can be a fraction. That's totally fine. There's nothing that bars n from being a fraction. The only thing that n can't be was -1, because that would result in division by 0. Okay, so let's continue on with this question. Okay, let's see. So let's just do all the standard establishing stuff. I'll do it on the left side here. So u is 1 plus tan theta. You could have tried, I think other people would probably try labeling secant as u, because secant in this case is raised to an exponent. But if you do that, it just won't work out, because it always has to be a function raised to an exponent with its derivative sitting next to it. So it's very specific how you kind of set these up. So we have u, we have n, it's 1 over 2. And now let's do du, and let's see what that is. So du, so what is the derivative of 1 plus tan theta? Well, the one part we don't have to worry about. The derivative of a constant is always 0, so the 1 just diminishes. And then the derivative of tan theta is, let me just double check, is secant squared theta, which is actually perfect because that's what we have that's what we got right here. So du is secant squared theta d theta. So it is in the correct format. It just didn't initially look at it. Another tiny issue in this integral is the fact that for whatever reason, you have a 2 just sitting there in front of the square root. Whenever you have a number in an integral like that, just sitting there, you can always take the number and move it outside the integral. And that's that's a maneuver you can do. And usually that's what I do, just to kind of like, there's this 2 and it's just like in the middle of everything. I just like to remove it from the integral, write it on the outside, and just leave it there and just deal with it at the end of the question. So that's what I'm going to do. So this is going to be 2 integral, and then let's write this in terms of u. So we got u to the 1/2, and we got du. Okay, so when you write it in terms of u, it really doesn't look too bad. And now we just apply the formula. So add 1 to the exponent and divide by that number. In this case, it kind of sucks because we got to deal with fractions. No one likes fractions. So add 1 to 1/2. What's 1 plus 1/2? That's 3/2, right? Yeah. So that's 3/2. And then you divide by that number. So again, kind of sucks. You got to divide by 3/2. Yeah, so divide by 3/2. But there's a trick I'm going to use in a second to make it look a lot better, because it's weird dividing by a fraction. Plus c. So far so good. Oh, I forgot about the 2. The 2 has to, yeah, we got the 2 sitting here. I'll just let it sit right there. That's what I meant when I was just like, just let the 2 just hang out for a while, and then we'll figure it out at some point. Okay, so let's continue. So dividing by 3/2, again, it looks super ugly. It's bad to divide by a fraction in terms of formatting, but dividing by a number is the same thing as multiplying by the upside down of that number. So dividing by 3/2 is the same thing as multiplying by 2/3. So that's kind of a neat little trick that whenever you have something that looks really ugly like this that you don't have to deal with, you can, so instead I can just get rid of the divide by 3/2 and just multiply it by 2/3. And again, this original 2 will just sit there and chill. So 2 is sitting there and chilling, multiply by 2/3, and then everything else is just the same. Okay, so finally we're getting somewhere. What to do next? So let's just do the numbers. We got 2 times 2/3. So that is going to be 4/3. I'm running out of room. So 4/3. 4/3 u to the 3/2 plus c. And now let's put u back in. U, if we look up, this is another reason why I always physically write down what u is. U is this one right here. It's 1 plus tan theta. So let's put that back in. And then we'll finally have our final answer. So 4/3, 1 plus tan theta raised to the 3/2 plus c. And that is our final answer. Hopefully that is correct. Yep, same as the textbook. So this kind of illustrates that sometimes you'll see a question and it won't really be obvious that the formula even applies to it. And most people probably don't know that a square root can be written as 1/2. So that's one thing that sometimes is unfortunate about these questions, where it's like all you require is that one tiny piece of knowledge just in order to change one thing in order to kind of recontextualize it. So if you're ever working on a question and you're stuck, just ask me. Don't get frustrated. Just send me an email and ask, because it might be a tiny thing that you're missing, and that's it. I remember in university, I had a rule that if I was ever stuck on something, I would never spend more than 10 minutes on it, because I found that after you spend more than 10 minutes on it, you're just kind of, there's other things you could do with your time. That was my rule, but yeah. Another rule was that I would only do 2 hours of homework per day, aside from my classes. I thought those were reasonable rules. So this was a good one. Let's see what else we have. What time is it? 10:08. Okay. I think we'll only do just this section today. Let's see. We could do this one. But first we have to go over, okay, so before we do the next one, let's go over another derivative formula. Let me just find it. So this is the derivative of ln. So ln is spelt like this. So it's a function, ln of x. It's a very, very fascinating function, ln. How in depth should I go into ln? Okay, so there's this thing in math called Euler's number. Euler was a Swiss mathematician in the late 1700s. He's my personal favorite mathematician. If you've never heard of Euler, which applies probably to everyone, go look him up on Wikipedia because he is so fascinating. He published 900 textbooks and articles over the course of his life. He was the most productive mathematician in history. It took them hundreds of years just to print all of the stuff that he created. And if you took his entire magnus opus, all of his work, it would fill 70 textbooks, and each of them would be 500 pages. And that was one person. And I also read it in multiple books, and they were like serious, well-researched books. And I'm trying to think of what the actual wording was. But apparently, if you took all of the science in Euler's century from all the scientists and mathematicians around the entire world, something about 1/4 of it all came from Euler out of everyone in the world in his entire century. Euler was a beast. He was crazy, and he had like 13 kids. So Euler was awesome. He founded like 3 areas of mathematics. He founded topology, which I got my master's in. He founded graph theory, which was just like a little thing that someone sent him. It was like a little map of bridges, and someone's like, hey, can you traverse all these bridges and end up at the original spot? And he was like, oh, this looks fun. Ooh, I just invented graph theory. Like Euler was super, super smart. Anyways, why did I go on this Euler rant? Oh, right, yeah. So there is a thing called Euler's number, named after Euler, and it is E. So this is probably a number you saw in the previous course. It's an irrational number, and it's roughly 2.718, and then it goes on forever. So that's Euler's number, and it's a very, very special number. Kind of similar to pi. You know how pi just like pops up everywhere, and it's super useful. E is also extremely useful. So E has this rare, unique property that it is its own derivative, and that's the only function that that's true for. As we've seen with all the derivatives we've taken, when you take the derivative of a function, it changes it, like the derivative of sine is cos. But the super cool thing about E is if you have e to the x and you take the derivative of it, it's equal to e to the x, which is amazing. It's a graph that is its own derivative, which means that at the rate of change at each point in that graph happens to be the actual value at that point in the original graph. So E is super amazing. It's super cool. Yeah, so that's E. And then you also have logarithms. And I don't really have time to jump all the way into logarithms. But basically, ln is a logarithm with a base of E. So yeah, typically when you have logarithms, like if you have the standard logarithm, it has a base of 10, but ln has a base of E. So ln has this special connection with this special number, E. So anyways, that's ln. And now we're going to look at the derivative of ln, which is a very easy formula. So derivative of ln is equal to, let me just double check this, is equal to 1 over x. So if you have ln of x and you take the derivative, you get 1 over x. Or you could write it as, in terms of, you could write it as dx over x. That's, in this context, that's practically the same thing. So ln, the derivative for ln, it's a pretty easy one to remember. And it's a super cool function. It's known as the natural logarithm. Okay, so that was a bit of a prelude for this example. So now let's look at the actual example. And maybe in a minute we'll look at, just for fun, maybe we'll take a couple minutes and look at Euler's Wikipedia page. Because he is, yeah, it's very fascinating. So this is another one where it doesn't look like the formula would apply to it, but it does. So this is ln x, and sitting next to it is dx over x. Okay, so one problem that I would, looking at this formula, one issue is I don't see any exponents. So that's probably one thing that could throw people off. It's like, well, the general power formula always has that n exponent. What the heck is going on here? Well, in this case, if you don't have a visible exponent, you technically just have an exponent of 1. So that's what you have in this case, and that's totally fine. Any number that doesn't have an exponent always has an implied exponent of 1. So all you have to do is just write it, and then it's like, oh, now it looks like the general power formula might work. The only problem was that the exponent wasn't visible yet. So in this case, u is ln x, n is just 1, which is fine. And then let's see if it's in the correct formula. Let's figure out what du is. So let's take the derivative of u. So derivative of ln, as we've just established, is dx over x. And surprise, surprise, that's exactly what we have in our integral sitting next to ln x. So it's in the correct format, even though it doesn't initially look like it is. So let me write this in terms of u, just so it's, okay, so this will be u to the 1 du. So when you write it in those terms, it's actually a fairly simple integral. And then apply the actual formula, add 1 to the exponent, and divide by that number. So u to the 2 over 2 plus c. Good, good. And then at the end, make sure you replace u with ln x. It always has to be in terms of what it originally was. So ln x to the 2 divided by 2 plus c. So that was a bit of a weird one. And again, it illustrates that these little derivative formulas, it's really, really good to know them or have them on hand. And after a while, it just becomes kind of part of the natural language of calculus. Okay, so that was an interesting one. Oh, and then there's another. Anyways, yeah, let's just for fun, let's look at Euler's wiki page. Just give me a second to bring it up. Okay, Wikipedia, Euler, Leonhard Euler. And let me, oh, I gotta share this. Share screen. Here he is. Euler also had, this is gonna sound weird, Euler also had a hilarious death. Lots of mathematicians have very funny deaths. I can say that because they lived a long time ago. It's fine. But Euler, I believe he had a brain aneurysm and he fell down and then he said, I die. And then he died. So Euler died very logically, just as he lived. He was completely on point about the fact that he was indeed dying, and then indeed he died. I just find it funny, the fact that someone would shout, I die, as they die. So Leonhard Euler, 1707 to 1783, a Swiss mathematician, physicist, astronomer, geographer, logician, engineer. So he was one of those people who did absolutely everything. Just like there was a mathematician called Leibniz who did like 30 different things. It's ridiculous. So he founded graph theory, topology, made pioneering and influential discoveries in many other branches, analytical number theory, which he also founded, complex analysis, infinitesimal calculus. He introduced much of the modern terminology in math, lots of the modern notation. Basically, all the math you see these days looks modern because Euler popularized all these different things. Like I think he popularized the symbol that we use for pi, virtually everything he popularized. Worked in mechanics, fluid dynamics, optics, astronomy, music theory. Yeah, I just can't believe how smart Euler was and how productive he was, especially since he had like 13 kids. Euler is held to be one of the greatest mathematicians in history and the greatest of the 18th century. And oh yeah, this is a nice quote by Laplace. He was a French physicist. He said, read Euler, he is the master of us all. Back then, master meant teacher. Let's see. Oh, even Gauss liked Euler, and Gauss didn't like anyone. And he's, like I mentioned, the most prolific mathematician in history. 850 publications collected in 92 volumes, including something called his Opera Omnia, which is presumably a big piece of work he did, or the entire collection of works that he did. So he's credited for popularizing the Greek letter for pi. So we always use this letter for pi. You can thank Euler for that. And a bunch of other stuff, but I won't spend too much time on this. So yeah, Euler is very, very fascinating. Let's see what else. I'm just trying to remember any other interesting things about Euler. Let's see. So yes, it was a brain hemorrhage. Yeah. Oh, and then he was also blind for like the last 2 or 3 decades of his life, but he still published like an average of like 1 math article per month. Like it was very, very productive. So this is all the stuff he did, popularizing all modern math notation, something called analysis, number theory, graph theory. This is how graph theory was born. It was just a little puzzle in regard to a town that had a bunch of bridges, and people were trying to like answer various questions about it, and a giant area of math came out of that. And then he did a bunch of other stuff: physics, astronomy, logic, music. He wrote a musical math book about how music is, a lot of it's based on math, but apparently no one read it because they said that it was too musical for mathematicians and it was too mathematical for musicians. He also wrote letters to a German princess, which were literal letters that he wrote to a German princess, but they were so well written that they were compiled into a textbook, and they were used as a teaching tool for like 100 years. So Euler, and then he also published some of the biggest textbooks of the time on calculus and analysis. So yeah, I always like reading about the great mathematicians, because they're almost like, their intellect was almost like a superpower that they had. He could also, it was documented that he could do math in his head up to 50 decimal places. So that's pretty cool. Okay, so that was a fun little Euler break. Let's, and then there's another funny, sorry, and then we'll move on, but there's a page of all the stuff that's named after him. Where is it? List of things named after Euler. And it's a ridiculous list. Euler's conjecture, Euler's sum of powers conjecture, Euler's, I can't pronounce that, Euler-Lotka equation, Euler's pump and turbine equation, Euler transform, Euler-Bernoulli beam equation. So much stuff. How could you have this many things named after you? It's still going. There's still other stuff. There's a planet named after him. There's a crater named after him. Yeah, I'll be lucky to have one thing named after me. Let's see. Okay, so let's continue on. That was enough Euler fun. Okay, so what were we doing? Oh yeah, let's do, we could do this last one. Let me try to find, yeah, this last one is a bit, we'll try this last one. It looks like a bit more of a challenging one, but let's do it. Let's get rid of this. And I think I'll probably have to establish some, yeah, in this case, we have an inverse trig function, which is pretty cool. So you have, let's do a bit of a spiel on inverse trig functions. So everyone knows the standard trig functions. You got sine, you got cos, and you got tan. And then you have like the reciprocal functions, like I'm always trying to remember, is it cosine? I gotta check. There's some stuff that I have a hard time remembering. Like, hold on. I think it's cosecant that's the reciprocal for sine. Where is that formula? I'm gonna trust myself, and I'm gonna say yes. So you got the reciprocal functions, like cosecant, which is just like 1 divided by sine. And then you got secant. Oh wait. This is so hard to remember these. I can never ever remember them. Yeah, I think you're right. Hold on, let me check my other formula sheet. I must have it listed somewhere. Oh yeah, it's probably on that. Okay, it's probably the trig identities page. Yes, yes it is. Okay, so sine is, yes, is cosecant, cos is secant, and then tan is cotangent. Okay, so I was right. Okay. Cotangent. So those are the reciprocal functions where, again, it's just like cosecant is just 1 divided by sine x, et cetera, et cetera. But then you also have what's called the inverse functions, which are functions that, how do I say this, that will reverse a trig function. So for example, let's focus on one actually. Let's just do sine. Let's say we have sine. Let's say we have something like sine x equals y. You could actually write this using something called the inverse sine function, which is just something that, again, reverses sine. So if you have sine x equals y, then you would say that sine inverse y equals x. It's literally just the opposite. So if you plugged something into sine and you got a particular answer, and then you plugged that into sine inverse, you would end up with where you originally were. It's different than the reciprocal functions because those don't actually reverse anything. You just do 1 divided by whatever the number happens to be. In this case, it's different that it actually completely reverses the appropriate function. And the formatting for this is not great because it says sine to the -1. So a lot of people assume that's an exponent, but in reality, it's just like a misnomer. It's just bad formatting. So when you see this exponent right here, it's not technically an exponent. It's just referring to the inverse sine function. A better format that they have is you can call it arc sine. And then that way, no one gets confused about whether or not that exponent is an actual exponent or if it's just part of the inverse function. So arc sine is better because then you don't have to have exponents that don't actually denote exponents. I don't know why they came up with that original notation, but yeah, arc sine is better. I'll try to use that. Although in the textbook they just use this notation right here. So that's unfortunate. So those are the inverse trig functions. So for sine, you got arc sine. For cos, you got arc cos, and then for tan, you got arc tan. Yeah, and then these also have derivatives as well. Let's look up one of these. Let's do the derivative for arc sine. Plus, it's fun to say arc sine. It sounds kind of badass. Okay, where is the derivative? Let's see. Okay, so derivative of arc sine. So I put an x. Yeah, I should put an x there. You always need your variable. It is, so this is listed on the derivative and integration formulas sheet. So this is equal to 1 divided by the square root of 1 minus x squared. So that is the derivative of arc sine, or the inverse sine function, or whatever the heck you want to call it. Okay, so I think that's all the prelude that we need before we do this one. I think we're good to go. Okay, and let's get rid of this. So the question is, and this is example 4. Okay, so we have an integral. In the integral, we have, I'll just use the format that they use in the textbook, despite the fact that it sucks. We have arc sine divided by the square root of 1 minus x squared. And then we got dx right here. And then we also have some upper and lower bounds on our integral. So just hold on. Sorry, just give me 2 seconds. Okay. Yeah, it has an upper bound of 0.5 and a lower bound of 0. And if people don't remember what what those bounds are referring to, that's something that you do at the end of the question. You evaluate the question as you normally would, and then at the end we'll deal with that part. Basically what you do is at the end, you plug 0.5 into your answer, you plug 0 into your answer, and you do first one minus second one, and then you get an actual number as an answer. So when they have numbered boundaries like that, your answer will be an actual number rather than a function. But we'll do that at the end. So this is another question where it's like, it doesn't even look like the general power formula would even apply, because we got arcsine divided by square root of 1 minus x squared dx. So this is one where you definitely have to rewrite it a little bit to see that it actually does work. So I think I'm going to rewrite this a little bit. Yeah. So we got the upper bound, lower bound. Those will just stay the same for the whole thing. I'm going to write sine inverse by itself, and then everything else I'm going to write beside it. And I'll put brackets around it. And I'll put, so dx on top, and then square root of 1 minus x squared. So it's the same as what it was. Sometimes it's good to just reformat it a little bit. So now it's starting to look a little better in terms of applying the general power formula, because we do have a thing and we do have its derivative sitting next to it. Because we just went over the derivative formula, and indeed that is its derivative. So this is another case where you technically have an exponent of 1. So let's do that. So let's put a 1 right there. Again, the -1 does not denote an exponent. It just denotes that it's an inverse trig function. Again, it's called an abusive notation. It's basically just crappy notation that they never really corrected. Okay, so in this case, let's establish everything, especially since this one's a bit messy. So U should be sine inverse. So far, so good. N is 1. And then du should be, so derivative of sine inverse. So we'll put the dx on top, and then on the bottom you get 1 minus x, square root of 1 minus x squared. So it is in the correct format. It's u to raise to the 1 with du sitting next to it. But again, one thing that's unfortunate about these is that you do have to have like a lot of solid pre-knowledge in order to kind of do these. So this is in the format. It's such a pain to write these bounds over and over again, but I guess I shouldn't complain. Okay, so it's in the format u to the 1 du. So after it looking so complicated when we originally got it, once you kind of recontextualize it and use your u and use your formula, it usually looks a lot better. And now let's just apply the formula. So add 1 to the exponent and divide by that number. So u to the 2 divided by 2 plus our constant. Always remember the constant. And now let's plug sine inverse back here, and let's see what we get. Oh, and okay, yeah, for now I'm just going to ignore the upper and lower bound. I don't want to have to keep rewriting it, so for now I'll just pretend it's a regular question, and then at the end we'll bring those bounds in. Okay, so this is sine inverse raised to the 2 over 2 plus your constant. So normally that would be the end of the question, but in this case we do have these. Yep. Yes, absolutely. Yeah, I was going to do that in a second. Yeah, so one of my students just pointed out that for the notation here, once you do the actual integration, and actually for this, you don't need the constant because it would cancel out anyways. So yeah, I'm going to erase the constant. You literally don't need it in this case. Eraser, goodbye, because it would cancel out regardless. So yes, exactly. The format for the upper and lower bounds is you put a straight line like this, you put a straight line like this, and you just write your bounds. And that's just a way of kind of keeping track of them. I didn't write that out of laziness. Apologies. And now what we do is we plug the top number in, we see what we get. We plug the bottom number in, we see what we get. And then we do first thing minus, or first number minus second number, and that will be our answer. So that is, when you see these numbers right here, that's what it's referring to. It wants you to plug them in at the end and subtract them appropriately. Okay, so this is going to be a tough one. So we're plugging in, man, this is going to be a weird one. So we're plugging 0.5 into sine inverse. So, and I don't like using calculators. I want to be able to figure that out for myself. Let's just write it down first of all. Let's just plug it in. So this should be sine inverse of 0.5 over raised to the 2, because everything else is the same. You just plug the numbers in for, like you plug 0.5 in for x. So over 2, and then minus, and then you do the same thing, except you plug in the lower bound. So that'll be minus sine inverse of 0. A lot of these are so ugly to write, over 2. Okay, so that's what it wants. Plug in the first number, then subtract, and then plug in the second number and see what you get. Okay, let's see. There's one part of this that will be easy. Sine inverse of 0 is just going to be 0, because sine of 0 is equal to 0. So it's just like zeros all around. Like, for example, here, I'll just write it. Sine of 0 equals 0. So it's kind of trivial that sine inverse of 0 also equals 0. That one's kind of, that's an easy one. So this part right here happens to diminish to 0. So thank goodness for that, because that makes it a lot simpler for us. So goodbye to that part. You're 0. You don't matter. Oh, that was mean. It's okay, buddy. You're important. You just are 0 in this case. And now the first one. So since that's 0, let's get rid of it. Let's simplify this. I'm running out of room. Okay, yeah, I'll just erase it. So goodbye to this part. That's a lot simpler. So now we only have to worry about this part right here. And again, so now we have to figure out what is sine inverse of 0.5. And I'm trying to figure out how we could do this in a practical way. Why don't we just start with the definition of sine inverse? Let's just start with that. And I'm going to need some room. But just note that, yes, this part, you could just use a calculator. Although your calculator might give you a decimal number, which is not great, because in this case, your answer is going to involve pi, which is an irrational number. So it's actually best to do this kind of like by hand. Anyways, let's try to figure this out. So I want to find out what the heck is sine inverse of 0.5. That's our main mission at this point. So let's just set this equal to, what should we set it equal to? I'm just going to set it equal to something, and then I'm going to rearrange it and write it in terms of sine and see if we can figure it out. I don't want to use x because we've already used x. Let's just use y. It doesn't really matter what we use. So we want to figure out what is y in this case. Now let's rewrite this in terms of sine. So this is the same thing as sine of y equals 0.5. So how does that help? Does that help us find y in this case? It's a tough one. So I think, and this could also be written 0.5 could be written as 1/2. I think in this case, we could use a special triangle. I think that's what we can do. Let's write down one of our special triangles. I'll try to squeeze it in at the top right here. Because because we have sine of y equals 1/2. We're trying to figure out what y is. And I'm recalling in my brain that one of the special triangles has a 1 on its side and a 2 on its side. So that seems like a logical place to go. That's the logic that I'm using. That's literally just like, hey, it seems like this triangle would kind of work for this. So the special triangle is, let me just make sure that actually this one's easy to remember. It is 1, 1. Oh, I already forgot it. Yeah. let's see. Yeah, 1 square root 2. Oh, so it looks like, okay, so this particular triangle doesn't work because it has a 1 and a 1 and a square root 2. So that doesn't work because we have a 1 and a 2. So we got to use the other one. So I was wrong. Apologies. We got to use the other one. Let's see the other one. The other one is so hard to memorize. So thankfully I have it right here. The other one is, it is, so 90 degrees right here, 30 degrees right here, 60 degrees right here. I'm hoping that we'll actually get the answer from this. I think we will. It's always fun to have a challenge. Square root 3 and 2. So that is one of our pre-existing special triangles. So, and then now let's go to SOHCAHTOA. So much stuff. SOHCAHTOA, all we need is the saw part because we're just dealing with sine. So sine is opposite over hypotenuse. Let me write that down. We're almost there, I promise. Sine is opposite over hypotenuse. So in this case, let's check some of these angles to see if any of them would work. Like if you picked 30 degrees, you would get opposite, which is 1, over hypotenuse, which is 2, which is exactly what we had right there. So it looks like 30 degrees is the answer in this case. That wasn't too bad. So like I told you, these special triangles are so awesome. So in this case, I basically just picked the angle that would give us 1 over 2, considering the fact that sine is always opposite over hypotenuse. And we did it. So that's good. Although I don't want to use degrees because degrees is, yeah, for your actual answers, especially with calculus, you want to use radians. So 30 degrees is, how many radians is 30 degrees? I think it would be, well, yeah, you're right. It'll be, yeah, but let's do this step by step. So we want to figure out 30 degrees in terms of radians. So I know that 180 degrees is equal to pi radians. That's kind of like a standard formula for converting between radians and degrees. So in this case, in order to get 30 degrees, you'd have to divide this by 6, and you'd have to divide this by 6. You always got to treat each side equally. And then you would get 30 degrees. So in terms of radians, it's actually going to be pi over 6. So that's not too bad. So yeah, you kind of just have to, again, there's a lot of pre-established formulas that you kind of have to know. So pi over 6, wow, that was so much work just to find the value of one number. That was way too much work. But pi over 6 is the answer for sine inverse of 0.5, but we're still not done. We still got to actually like plug that in, because what we're actually concerned with is this whole thing right here. But at this point, it's at least a little bit easier. So sine inverse of 0.5 is pi over 6. So this is going to be pi over 6 squared over 2. Let me just check. Yep, so far so good. Still running out of room. Let me just erase some of this. And then this will be our last question, since we covered, this is definitely a big chunk that we've covered. So we'll finish early and we'll call it a day. Yeah, either we'll take a break if we're going to do the full 2 hours, or we'll finish early. But everyone's always free to request a break, even if we're finishing early. Okay, so we got something, kind of an ugly expression, pi over 6 squared divided by 2. So whenever you have a thing over a thing squared, you can apply the square to both the numbers. Because this is, yeah, it's pi over 6, all of it's squared. So what you can do is you could write the square attached to the pi, and you could write it attached to the 6. And that's exactly the same thing. And then the 2, oh, this is going to look really ugly, but the 2, I guess, can just sit at the bottom. Yeah, that looks horribly ugly, but oh well. So let's simplify this a little bit. In this case, because you have this 2, you have like a triple decker fraction here, which is really weird. What you can do is you could just take the 2, basically get rid of it on the bottom here and just put it up at the very top. That's a perfectly legal maneuver when you have like the triple decker fractions. You can just take the very bottom number, put it up at the top, you're good to go. So let's keep simplifying this. Let's see. Okay, so pi squared will just stay as pi squared. Oh, actually, hold on. I might have made a mistake. Well, they end up with something a bit different than what I'm going to end up with. I think yeah, sorry about this. I made a small mistake at some point here. Yeah, this 2, that's a tough one. Okay, so. Okay, sorry about that. The 2 should not join the pi at the top. It should join just the bottom number. Yeah, sorry about that. That was my mistake. So in this case, we're almost done. Pi squared just sits there. Pi squared, you can't really do anything with it. You could go on your calculator and figure out what it is as an actual number, but there's no point in doing that because it's an irrational number and it's not like you can write down infinitely many decimal places. So it's better just to write it as pi over 2 because then it technically encapsulates all of pi. So it's always best just to write, yeah, just keep it like that. And then at the bottom, we have 2 times 6 squared. So 6 squared is 6 times 6, which is 36. So 2 times 36. Nearly done. And then we got, so pi squared. And then at the bottom, you'll get 2 times 36, which is 72. So that is our official answer for this one. So that was definitely a tough one because there's, you got the upper bound, you got the lower bound, you got trying to figure out what the heck is sine inverse of 0.5. The reason I didn't want to use a calculator for that is because I wanted my answer to look like this. I didn't want an actual decimal number because it'll never be as accurate as this answer because this answer has the actual symbol pi. So yeah, in general, when your answer has pi in it, I would usually just keep it as pi and not figure out the actual number. Yeah, but if you do, like in this case, for example, just for complete illustration, if you really wanted to, you could go on your calculator. You could type in, where's my pi button? Pi squared, it equals, divide that by 72, it equals, and you could get an actual number. The number in this case is 0.1370777838. But this original answer is so much better than this answer. First of all, this number, I mean, it's just a random number. It doesn't add anything to include the actual number. But this one is so much better, again, because pi is irrational. The only way you could actually include all the digits of pi is just to write down the symbol for pi. Yeah, but just in case anyone gets an actual number, if for some reason you go on your calculator, you want an actual number for your answer, just try to include at least like 6 decimal places, just for accuracy. Okay, so that was a lot. At least it was only one formula. So yeah, does anyone have any questions? Okay, I'm going to stop sharing. Does anyone online have any questions? And let's see, are we still recording? Yep, good. Okay, I think I should give, oh yeah, I should give one of these, I should give a participation question. We should start with those, and then we'll conclude the lesson. Let me just grab a pen. I had a pen here somewhere. Here it is. Okay, let's do, I'll give you 2 questions and we'll take them up next Tuesday, and you just have to have them in by then. So remember, these are just the participation questions. I'll activate Dropbox and then you just submit them before next Tuesday, and then we'll take them up. And you just have to make an effort at them. You don't even have to get the right answer. So that's kind of nice. So let's pick 2 questions. Let's do, trying to find ones that are not too bad. Okay, let's do number 3 on page, actually, and I'll write down the actual question as well, because last time people had a different version of the textbook. Okay, let's get rid of this. So let's do, so this is page 851. 851, number 3. This question is practically like a giveaway because it's virtually the same as like the very first one we did. It's just a different exponent. Like it's, yeah, that one's definitely a generous one. And then let's do a slightly more difficult one. Let's do number 6. Oh, let me write down this first. So number 3 is integral of sine 4x cos x dx. So again, almost the same as the previous question. And then number 6 as well. And that is integral of 8 sine of 1/3 x cos x dx. So just those 2 questions, just give those a try, and then we'll take them up. And let me just circle these so I don't forget number 3 and number 6. So I'll post this under news. I'll activate participation number 1. Everyone work on that. I also think I'll post the first assignment just so everyone has an opportunity to look at it. You won't be able to complete it because it has this and it has another topic, but there's no harm in just having it up early. So no due date for that yet, for the actual assignment. But again, these ones are due on Tuesday. Okay, so I guess that is everything. So everyone, thank you for coming and have a good day. And I will virtually see you on Tuesday, and have a good weekend.